Uh, Welcome everyone to the AAVSO webinar series. My name is Bert Pablo, and I am the staff astronomer for the AAVSO. I'm so glad that all of you could make it on this, well, for me, very snowy Saturday. If you're wondering why the new face, our normal host, Lauren Harrington, has left the AAVSO to focus on college. And on behalf of the AAVSO, I want to wish her well on her new journey. Today, we're going to talk about the Supernova Early Warning System, the AAVSO's current endeavors in support of it, and how you can get even more involved. But before we dive in, I have a few quick announcements to make. First, we are running in Zoom webinar mode today. For those of you who are unfamiliar, this means you get access to a few special features. First is the chat, where you can introduce yourself, as most of you have already done. Second is the Q&A button, which you can find at the bottom of your screen. If you click on the Q&A button, you can type in questions for the panelists, and I highly recommend you do just that. Note that we will have multiple speakers today, so if your question is intended for a particular speaker, make sure you include their name where necessary. I would like to point out to please put all of your questions for the speakers in the Q&A, because as you can see, sometimes the chat can get overloaded and it's very difficult for us to follow, and we don't want to miss any questions. Finally, there is the CC button. Zoom will do automatic captions, so you can click on this button to enable the captions if you think it will help you. Please note that since the talks are in English, the captions should also be in English. If you try to put them in a different language, it will try to figure that out in that language, and it will not be very helpful to you at all. Sorry, one second. Next, I'd like to express our gratitude to our 2025 series sponsor. Voice Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at voice-astro.org to learn more about their offerings in astrometry, photometry, and spectroscopy. Support from sponsors like Voice Astro and donors make the work of the AAVSO possible. To support the AAVSO, please consider a donation by scanning the QR code on your screen or going to aavso.org. All donations are tax deductible and support our mission of enabling anyone, anywhere to participate in scientific discovery through variable star astronomy now and for generations to come. And now, on to our presentation for today. Our main speaker is Dan Milisavljevic. He is an associate professor at in the Department of Physics and Astronomy at Purdue University. He completed his undergrad degree in the liberal arts at McMaster University, a master's degree in philosophy at the London School of Economics, and a PhD at Dartmouth College in physics and astronomy. Prior to Purdue, he had positions at Harvard University and the Smithsonian Astrophysical Observatory. Milisavljevic's research interests include how stars evolve, extreme physics associated with exploding and disrupted stars, and the formation of dust and molecules that seed the universe with the building blocks of new stars and planets that may harbor life. Milisavljevic has published over 175 scientific papers and has been interviewed on CBS 60 Minutes, CNN, and NBC News about his most recent work studying supernova remnant Cassiopeia A with the James Webb Space Telescope. And with that, I will turn the screen over to Danny and let him begin.
That was wonderful, Bert. You nailed my last name. Very good. Thank you for the invitation to be here. I wish I could see you all, but I feel your energy. I love the chat comments coming in. Let's get started. Let's see here. I can share my screen. Yeah, I always draw inspiration from your members, and it's such a delight to be here today. Some caveats. So, well, first of all, I'm here to talk about the Supernova Early Warning System and to focus on catalyzing discussion on what our response strategy should be. There's going to be a lot of science, exciting science, that I won't be able to go into detail that Alec Habig covered in his talk last year. So I encourage you to go back and watch that yourselves. I'll touch on that so that for those people who haven't seen it, can be aware of the context of the importance of what we're trying to do. It also provides motivation and will guide our discussion about what the most efficient way to respond to this is. Okay, without further ado, I'm going to move forward, and I'm going to start with kind of a bombastic statement. Okay. I want to say that the next Milky Way supernova will be among the most important events of the century. Full stop. Okay. And I think that as citizens of the universe, it's our duty to study this nearby supernova as completely as possible. Okay. And I think that in this crowd of people who are interested in things in the sky and have access to tools to study it better than, say, a general population, we have added responsibility to do so, okay? Because we have means greater than others. If you look at history, it's really demonstrated that supernovae have been pivotal events. Okay? What we're seeing here is an etching of famous Danish astronomer Tycho Brahe observing the supernova of 1572. Yeah. Supernovae in our own galaxy become very bright. It's no surprise. Okay, they can get to a luminosity that's billions of suns. Okay, and so with that, they become visible for many months to beyond a year, and they can even sometimes be visible during the day. Here I'm showing a reconstructed light curve of that supernova of 1572. You can see here that it's peaking at around -14.5. So if any of you have gone out to see Venus recently, it's screamingly bright right now at around that same magnitude. So imagine something like that coming into a new source in the sky. This is, by the way, what the debris field of that supernova explosion looks like, what we call a supernova remnant. Okay. This particular explosion was the result of a white dwarf progenitor system. That's different from the type of explosion that the Supernova Early Warning System is going to be sensitive to, that comes from a massive star explosion. And that's what this is representative of. Okay. Bert mentioned my James Webb program, observing Cassiopeia. That's what this is. So Cassiopeia A. In the constellation of Cassiopeia, it gets the name A because it's the brightest first radio source determined. This is the last known galactic supernova that was of core collapse origin, which means that the star that was there beforehand was a massive one. Okay, we think that the progenitor star of Cassiopeia was between 15 and 25 solar masses. We think the year that it exploded, relative when the light first came to Earth, was around 1680. There's no credible historical account of that. By following the motions of the ejecta with time, so this is the debris, it's moving at 5,000 kilometers per second, so we can trace back its origin point, and we estimate that it happened sometime around 1680. Okay? If supernovae happen at a rate about 1 to 2 every year in a Milky Way galaxy, we are overdue for a next galactic supernova. Okay? And even in more broad strokes, understanding why is this important? Well, supernovae are a fundamental process in the universe. Okay, they drive cosmic evolution. They do this in various ways. Stellar death can actually produce new stars as the shock waves interact with molecular clouds that trigger new star formation. They are a significant source of dust, which are the building blocks of stars and new planets. And, maybe most important for us, they manufacture the heavy elements. So, of course, the iron in our blood, the calcium in our bones, the oxygen we breathe, and of course, the carbon in our apple pies. Okay, these are all being manufactured in supernova explosions. So, one, if you haven't done so already, please go to the SNEWS2.org website and join the alert list. Okay, this will get you on the email list to let you know when the big one happens, the next one. Okay, what I'll be advertising today here is a subset of this, a specialized group that will be helping with the response strategy. So I'll show you the context as we move on. But number one, please visit SNEWS2.org and consider joining that alert list. And for the rest of the session, I'll be talking about the fire drills, which is to say the practice we'll be doing to coordinate a response to the next supernova as well as possible. Now, how is that going to happen? How are we going to know when that galactic supernova happens? Well, the history of that goes back to this star in the Large Magellanic Cloud that you can only see from the southern hemisphere, Sanduliac minus 69202. Now, the star itself is not spectacular. You can see other stars of equal brightness and even brighter stars in the top left there. But of course, the arrow means something. And indeed, in February of 1987, that star exploded. Okay. How did it explode? Well, the star begins as a big ball of hydrogen, helium, and some other trace elements. It goes through successive stages of fusion at its core. It builds up this onion interior. When it reaches iron in the core, we lose that radiative pressure that holds the star up, and gravity takes over, and it crushes all this nucleosynthesis that's happened over millions of years into neutrons and electrons and protons. Okay, that process of collapse, and then the rebound that happens as these particles get so close they can't get any closer that physics will allow. Okay, it produces a lot of neutrinos, these subatomic particles that normally pass through unimpeded. Okay, but at the intense densities of the core of this explosion, they can actually help in the explosion of the star. Okay, so for many decades, the simulations always showed a collapse, and certainly a collapse can proceed to form a black hole, but we know that the explosions must be successful some good fraction of the time. Example, 1987A. So it's the neutrinos that provide a lot of energy. Now, how much energy? 10 to the 53 ergs approximately. Put that in context. If you take all the energy output by the sun over its entire 10 billion years, and then you multiply that by 100, that's the amount of energy that the supernova will emit in neutrinos in 1 second. Okay? It's a whole lot of energy. And it's these neutrinos that come through that facilities on Earth can be sensitive to. Okay? When this supernova 1987A happened, facilities at the time were able to detect about 20 neutrinos. With advancements in facilities and scale, we now anticipate detecting thousands of neutrinos from the next galactic supernova. And this opens up a lot of exciting science opportunities, okay, that I don't have time to go into today, but I encourage you to look those up. So, working with this knowledge, instead of just passively waiting for those neutrinos and then realizing a supernova is happening and then looking back to see if there's excess neutrinos associated with a supernova, the strategy is to be proactive, is to constantly be listening for when that flood of neutrinos hit their tanks, as it were. Okay, And to have greater confidence in when that's happening, neutrino facilities around the world have networked together. So that, let's say, in an extreme scenario, in a distant and or weak supernova, the neutrinos are produced, a facility may have some weak detection. Alone, it will not have confidence. But by networking multiple facilities that can all have a shared acknowledgement that something's happening, together there's a much greater confidence to announce to the world that something is going on, that there's the next galactic core collapse supernova. Okay? Neutrinos have the advantage that they arrive ahead of the electromagnetic fireworks display, okay, the stuff that we'll be interested in. Okay? This is a log plot, and there's a lot going on, but try to understand basically these terms. Up top, we see the neutrino light curves. You see how much stronger they are in energy compared to the electromagnetic radiation in black, but also the time scale. Okay? And if you convert these seconds in log time to human measures, it's about minutes to days after that initial neutrino burst that signals that core collapse, when the iron core of the massive star is collapsing. There's any time frame depending on the size of the star, how extended its envelope is, how much mass loss there is surrounding the star. There could be any time frame from minutes to many hours to even potentially days from the neutrino burst that floods the neutrino facilities to when we will first be able to see some change in the star at its surface. Okay? That has to do in part to the progression of the shock wave. So there's the collapse, there's a rebound, and then there's a shock wave that's progressing through the star. Okay? And that can take some time frame. And then the red supergiants in particular have very complex convective photospheres, and that can actually change the time scale as well. Okay? But let's just phrase it differently. That means as us as observers, we have an uncertain time frame that can be as short as a few minutes to somewhat more relaxed, but still brief days later from when that the star first shows in electromagnetic waves that something is happening. This is maybe another plot that summarizes it even better. So it begins with the neutrino burst, which itself has a duration of about 10 seconds. Then we have some delay, as I was emphasizing there, from when the neutrino burst happens to when we see the first indications that something's happening with the star in the electromagnetic spectrum. That's minutes to days. And then this process of shock breakout. I'm going to have a slide or two more about this. The emergence of the shock wave from the star is accompanied by a very bright UV X-ray blast, a shock breakout. And that in itself can last anywhere from seconds to hours. And that shock breakout duration encodes very important information about the star, what it's like, how corrugated the surface is, how extended it is. Okay. So the question everybody wants to know is, what star is going to explode next? Barry Poynton always wants to have a lottery. You know, everybody put in what their favorite star is, and let's have some kind of friendly wager about which star is going to explode next. You hear Betelgeuse a lot in the news, but clearly, or not clearly, it's most likely not going to be any star of our favorites. But anyway, to help answer that, Sari Healy at Virginia Tech, grad student working under Shunsaku Horiichi, developed a catalog of red supergiant stars in our Milky Way galaxy. This is not easy, okay? Classifying red supergiants themselves can be a challenging prospect, but then the intense extinction that, as you're looking through the disk of the Milky Way, can obscure your ability to completely sample all the red supergiants. But she did a Herculean effort to catalog as many as she could, and we're in the region of 600. And here they are plotted. For no surprise, It follows largely along the galactic plane. You can see here and here. Okay? So we don't know which star will explode. We can't, by observing the star, have a sense of which one is closest to core collapse, but we can make educated guesses. Okay? And this catalog is a kind of a good basis to start from, where we would try to find which star is exploding if we were to have a SNEWS alert. Okay, so let's start talking strategy. What are we going to need to do? So the phase one is just noticing that something's happening. This comes from the SNEWS alert. So if you sign up at snooze2.org, you'll get the alert that something's happening. Okay. Our upgrade from the original SNEWS that started in the early 2000s to SNEWS 2 today is more information, which is to say, by using timing information from when the neutrinos arrive at the different facilities, we can do a localization, okay? Kind of like the LIGO Virgo facilities do for gravitational wave follow-up. Okay? And there's various strategies of whether you want to do a wide, shallow survey or narrow targeted. I just told you we have these candidate stars. That's a good start, but the universe never plays nicely. And it's very possible that the star that explodes isn't in that catalog. So we have to have a combined strategy that has some wide field ability that isn't just looking at these specific stars. And then another phase comes sometime later. The hope is that by running through the neutrinos with our models of what types of stars give different neutrino light curves, we can actually make estimates of the mass of the star and the distance, further informing which stars could be likely candidates. So it would help us, for instance, know whether it's within, a couple kiloparsecs, or it's a distant 10 kiloparsecs on the other side of the galactic bulge. That would be much more challenging for an optical discovery. So part of today's discussion that we're going to have following the talks is to outline what that strategy will be like. At the moment, we're in the middle of testing a new feature of SNEWS 2 that cross-matches the Healy catalog with a localization that could be made through multiple neutrino facilities that could be operating any time. On the right is a very optimistic, sometime in the future, if we could get localizations this good. On the left is something more likely to happen in the near future. And here in black, you see the candidate stars plotted. This is the localization region, okay? So you'll see here some overlap again with the gravitational wave follow-up. You have a localization region, and in that case, it was a galaxy catalog with distance, okay? In our case, the neutrino localization will likely not be nearly as good, okay? And we will not have a catalog as complete as the galaxies, as the gravitational wave community has, okay? Our end goal is to automate sending out recommendations to observing agents and optimize the response strategy via coordination. Okay? And part of this talk is to let you know that we need your help to make the system as efficient as possible. And we also want to begin a lot of practice. Here's a map of the world showing where the neutrino facilities are located, but also more importantly, location of AAVSO members. Okay. AAVSO brings a real, a unique strength to this follow-up campaign, and it can do things that the professional community can't. Okay, if anybody has experience in time domain astronomy, geographic diversity, okay, and strength in numbers always wins out. Okay. The nearest supernovae extragalactic that are found are often by volunteer amateur astronomers, just because they're constantly looking at the sky and they aren't afraid of air mass, right? So having that constant surveillance in the sky is a real strength, that this kind of geographic diversity and strength of numbers. So for instance, weather can be a real issue. Professional observatories are located in specific regions, whereas members of AAVSO are much more well spread out. And there's redundancy. If somebody's equipment isn't working, somebody else can pick it up. And then there's also the issue of saturation. Many of the professional observatories will be saturating, especially the all-sky surveys, at objects brighter than 10th magnitude. Okay? And that's going to cover a lot of the stars that we're interested in. And it's going to cover, if you saw there, it could get to minus 4.5. That's not something that professional observatories can do. Oh, we also want to avoid bunch ball. So if you ever watched a soccer match of young children, their inclination is to all chase after the ball. Well, that happens in time domain astronomy sometimes too. We all want to go after the next bright, shiny thing. Okay. The importance of this event, which could happen in the next few minutes or years from now, okay? We don't all want to be chasing Betelgeuse, for instance, okay? We need to divvy up the responsibility as best we can, okay? And I want to discuss strategies that we can use to best do that. Okay? I'll be advocating a strategy that kind of mitigates risk. So one, this recommendation list where members have intense monitoring of likely candidates. And I think the best way to work through redundancy, to incorporate redundancy, is intensive monitoring of patrolling of multiple stars. We may all have our favorite stars, and some of us may only want to choose one star, okay? But we have to at least make sure that not all of us are choosing one star. And if we do choose one star, if that night I happen to be on vacation with my significant other and I'm not able to get to my telescope, somebody else needs to be filling in. Okay? So patrolling of multiple stars is a good way that we have redundancy. Okay? But then, of course, as I said, it's very likely that the star that explodes isn't in this catalog, this supernova candidate catalog. So we need a wide and shallow monitoring of the star as well, of the sky as well, to be prepared for the unexpected. So this presentation is about SNEWS alert follow-up. George and Bert will be talking about the monitoring campaign that is looking at a subset of these candidate stars to develop a light curve, a historical light curve that would be very important in understanding the whole core collapse process, rich science. It also helps you to get familiar with certain stars that may explode so that when the time comes, you can jump on it immediately. Okay, I wanted to do about 40 minutes of talk. I got a little bit, about 10 minutes left. Let me give you a little bit more sense of the science that we're trying to do. This will help guide the strategy. Shock breakout is incredibly science rich, but it's incredibly hard to see. Okay? It's a brief time of the explosion. It happens when that shock from the original core collapse and the rebound of the protoneutron star, okay, as it passes through the interior of the star and then emerges at the photosphere. Okay? That time frame has never been measured precisely, which is to say, supernova 1987A told us when the neutron burst happened, but we never measured shock breakout. And then in a couple slides, I'll show you serendipitous times when we happen to capture the shock breakout, we think, but the supernovae were too distant to capture the neutrinos. The explosion of a supernova in our Milky Way will give us the opportunity to measure precisely neutrino burst with core collapse and the emergence of shock breakout. And more so than that, it's not just a number, but it's a timing, how long that shock breakout proceeds. In the optical, we see a subset of the energy. As I stated, most of the energy is going to be coming out in the X-ray and the ultraviolet, but there's still important information that we can access in the optical in terms of timing. Okay. Let's see. Oh, I said here, yes. Valuable information about the structure of progenitor star and its mass loss history is encoded in the shock breakout. On the left here, I'm showing a simulation of a red supergiant where the shock is passing through. And you have to appreciate that the red supergiant is not spherically symmetric. It has these very deep convective cells. There's incredible mixing. Okay, so the shock propagating through. Okay, when does it emerge? Well, when optical depth equals 1, but in one direction. In what direction? Okay, there's a lot of nuances in that timing of how long that shock breakout duration is. And for all we know, that time scale may be hours or days for a red supergiant, depending on how extended the envelope is, how much the mixing is, and how much mass loss there is in the immediate environment. If that red supergiant has had extensive mass loss, it'll take time for the shock to move through the dense mass loss to a point at which the electromagnetic radiation emerges. But bear in mind, it may not be a red supergiant. 87A was a blue supergiant. Okay? And in that case, although we did not measure shock breakout, we do have an upper limit to when light first arrived of about 3 hours. So after the first neutrinos that were detected. Okay? So again, depending on the star, it may be hours. It can even be minutes if it's a compact star, Wolf-Rayet star, for instance. Okay? A blue supergiant was in terms of hours, and a red supergiant could be as long as a day or more. Here is a Kepler light curve of what they interpret to be shock breakout from red supergiant. You know, Kepler gives us these incredible time-intensive measurements of a light curve, and you can see that it's a tiny blip from the overall maximal brightness. Okay, this again is a reflection of what I stated earlier. It's X-ray and UV where you see most of the energy coming out of a shock breakout. But nonetheless, this is still incredibly important to know when that happens, the shock breakout and the width, the duration of the shock breakout. Okay. And a shout out to Victor Busso, who, if you don't know the story, he had a new camera that he was testing out on his telescope. He just pointed the telescope to the galaxy that was overhead at the time, kept running through test exposures, and just serendipitously happened to capture that shock breakout happening in a supernova in an extragalactic system. Great story there. That was 2016 GKG. Okay, so some review here. It's likely we won't know which star will explode before shock breakout in a large field of view. So intense monitoring and recording that information is important. So, which is to say, you may not know that it's happening in real time. It may be fairly subtle, but recording that information is vital. Okay, so you need to make, if you're recording a movie of wide field, make sure that the sources are not being saturated and that the recording is happening. Okay, so it's one thing about having bragging rights about finding which star happens first, and it's great if you can, but it's most important in at least having that constant recording taking place, because that change for shock, that change attributable to shock breakout may not be obvious. Okay, and I'll emphasize there again at the bottom, the precise timing between when the neutrino burst happens and shock breakout has never been made before. This is something that the AAVSO volunteer astronomer community can provide better than the professionals. This is something that I desperately want us to be able to do, but we're going to need to work together and we're going to need to have practice. Okay. I'll advertise some of the tools that we have in getting the word out. We have a mobile app that you can get for iOS right now. It's in a beta form. It's been working fairly well. An Android version is in advanced development. These are designed to get your attention and provide information about the alert. It's a nice, common user functionality where it helps you point with your phone where in the sky to look for the supernova using the triangulation information provided by the neutrino facilities. And then I'm just noting here, it's always been in my interest. I just haven't had the bandwidth, the time to have a collaboration with Astro Calibri. And another one that was in discussion, but again, not enough bandwidth, there could be a unistellar connection as well. So if a SNEWS alert goes out, it could be alerted to unistellar users, and a suite of telescopes could be looking on it automatically. Okay, so what we want to do is have fire drills. And these are just routine practicing of response to SNEWS alert. And we really want to follow, in many ways, the model set up by the gravitational wave community. They learned a lot through repetition on how to follow up alerts. There's overlap between what our needs are for core collapse supernova and the gravitational wave community, but it's not precise. There are unique needs for us, especially in terms of our catalogs are incomplete nearby. We have such a range of potential brightness from near saturation to barely observable. Okay. I will mention here that Grandma is a collaborator. In case you haven't heard, that's the Global Rapid Advanced Network devoted to multi-messenger addicts. So they are a collaborator. Some users here may be users of that. We're dividing up the work such that they will take care of coordinating users in a tiled manner. But I'll move on beyond that. Fire drill is planned for approximately late March, but most likely April, to practice this, okay, and assess the capabilities of participants. And as we anticipate, it's likely we'll give you a 1 to 2 week window of when to expect an alert to be distributed along with instructions. This first pass will emphasize intense monitoring of candid stars, but we want to know about observers with wide field monitoring capabilities and what can be done. George briefly showed me a cool setup that he's going to discuss along that. The alert will also be distributed via email and mobile apps. And I mentioned that. Volunteer astronomers can play a pivotal role in monitoring stars below 10th magnitude that saturate most professional facilities. This is also very good for users of binoculars. Okay. The eventual goal is to have approximately 2 fire drills per year. We'll have regular meetings, so debriefings where we have opportunities to share the experiences and recommend strategy adjustments. And we want to start hearing from you about, are you a visual observer? Do you have a telescope? Is it robotic? Is it remotely operated? The default strategy will be for us to send a list of recommended stars to patrol, but what else should we consider? Maybe if you'd like it in some specific target format for whatever software you use. What kind of communication should we have between observers? The Slack channel may be one. What other considerations should there be? VO events is something we've used with some of participants in our refit pack project. Chuck Cinnamon I think I saw online he's one of the ingesters of that with his ACP scheduler software. That's something else that we're investigating. Oh, there's a quick flash. If you want to practice for the next galactic supernova, one good way is to look for extragalactic supernovae. I help manage the refit project. That helps. You can log on, and it's like a Netflix for the sky. It tells you what are cool supernova you can try and observe. Again, this is extragalactic, but the process of getting a recommendation, aligning on it with your telescope, taking good data, and then reporting it back in is a good procedure to practice. And this is one of the projects that can help you do that. All right, I think I'm going to end with another one of these bold statements, okay? Rich scientific opportunities will be lost unless there is a worldwide cooperative effort to coordinate observations of the next galactic supernova. And I've been trying to emphasize again and again that AAVSO has the geographic diversity and large numbers of of small aperture telescopes that are needed to complement professional observatories that may very well be blindsided by a galactic supernova. They'll be scrambling to baffle their telescopes. They'll be scrambling to change their setups. Okay, that will be valuable time lost that the volunteer community can do. So I'll flash some conclusions. I've already stated a lot of this before. You can join SNEWS at that website, but most importantly, let's start practicing. And if you're interested in the SNEWS fire drill team, there's a quick survey that you can do where you put your name and email address, and you'll be put on a mailing list that will be sent out to let you know about upcoming fire drills and community meetings that we're going to have. And with that, I'll stop and I'll pass it on to Bert and George.
Thanks, Dan. I have a few questions, and I think what I'm going to do with the questions is let you answer the science questions, and we'll leave the sort of more other questions about getting involved and stuff to the end. So I will try to get a reasonable subset here and answer the rest as we come. The first one is, and this was from the beginning of the talk. I'm not really sure exactly what the context is here, but it says, why is there no explosion under spherical conditions?
Oh, well, it comes down to, so there is what they call the prompt shock that's initiated as the core rebound. So you had initially an iron. I'm going to go into lecture mode. I'm going to try and condense it into a couple sentences. That shock that comes from the rebound. So the neutrons, and there's some electrons and protons in there, but mostly neutrons, they get to a point at which the strong force says, you can't get any closer. And there's a bit of a rebound as that happens. That rebound sends a shock wave that will originally was thought to disrupt the star. But the simulations that tried to reproduce that in spherical conditions always found that that shock wave would stall because of the infalling material about the rest of the star. So the collapse happens at the core region, but it takes time for the rest of the star to realize something's happening, and then that collapse happens. So there's material from the outer, the mantle of the star that's falling inward into the core. There was the shock wave that's initiated, but there isn't enough energy in that prompt shock to overcome the infalling layers. So what simulations have, and various simulations have attempted various strategies, maybe magnetic fields, maybe neutrinos, but all of them find that the breaking of spherical symmetry is a necessity to allow that shock to propagate through the star and allow the explosion to take place. The most favored interpretation is that the neutrinos alone have enough oomph, enough energy to impart on that shock wave to revive it and push it through the star. And because it's so complex and we have this sloshing motions, there'll be uneven heating by the neutrinos on the surrounding layers that produces the asymmetry needed to explode the star.
Okay. Thank you for that detailed answer. The next one is, and I sort of know the answer to this, but I'll let you do it. I may have missed it, but how many minutes or days did neutrinos arrive before we visually saw 1987A?
Oh, it was in there. The first observations happened a few hours after the neutrinos. Yeah,
Cool.
but there was no observation of the shock breakout, as it were. So that's why it's just an upper limit. So we know the first light that we saw detected here on Earth was a few hours after those neutrinos came in.
Do neutrinos travel at the speed of light?
Well, neutrinos, we believe, have a very slight bit of mass. So that means they can't travel at the speed of light. So they travel near the speed of light.
Why is the early warning system only interested in core collapse supernova?
Hey, great question. Very good. And I kind of danced around that. It will really suck if the next galactic supernova is a type 1A or the ones that are associated with white dwarfs, because they don't produce nearly as much neutrinos. Okay? Don't hold me to actual numbers, but I know that it would need to be a very nearby system to detect the neutrinos from a type 1A explosion. Okay? There's just that process of collapse from the iron core down to the proto-neutron star that produces copious neutrinos. In the case of a type 1A explosion from a white dwarf, you don't have the same process. This is like a thermonuclear ignition of that carbon-oxygen white dwarf, and it's just not associated with nearly as many neutrinos. Now, who knows? In with the network capability of SNEWS, perhaps they would still be able to see something with confidence as they share their information. But nonetheless, we get our most bang for our buck out of a supernova if it's a core collapse explosion.
Okay, I think I will do maybe two more questions and then we'll probably have to move on. And I will get to the rest of them at the end, hopefully. The next one is, what is the difference between red and blue supergiants that go supernova? Why are we focused on the red ones for SNEWS? Should we be adding blue ones as well?
So it comes down to temperature. That's the simplest answer. Reds are cooler, blues are hotter. They're at different stages of stellar evolution. We think the blue supergiant that led to supernova 1987A was actually a merger of two stars. Lots to say about that, but you're 100% right. There are other types of stars that may give way to supernova explosions. Sarah started with red supergiants, which are the most abundant producers of core collapse supernovae. But absolutely, they can be blue supergiants, as we find with 87A. Actually, it was a funny moment in history. For decades, theorists had predicted that red supergiants were the natural progenitors of core collapse supernovae. And then the first time we had a confident pre-explosion detection of a star, it was a blue supergiant. And what did the theorists do? Well, they started retroactively predicting that blue supergiants could be core collapse explosions as well. And now, since then, we've actually found that yellow supergiants can be progenitor stars of core collapse explosions as well. So Sarah Healy, with others, is looking to expand that candidate catalog to other types of stars as well. She just started with red supergiants to keep it a kind of clean search, but that catalog is being expanded upon.
Okay. I think we still have some questions, but we'll get to them at the end. And I will give a very, very brief sort of mention of the other part of this project. And then I will pass it on to George, and we will move on as quickly as possible to your questions. Now, let me go to slideshow and play from start. Cool. So I only have 3 slides. The first one is just simply what the project is. So as Dan mentioned, we are doing a subset of stars and trying to get light curves on as many of them as possible over long periods. Now, why did we choose this subset? Well, because these are the brightest stars, which means that they are the easiest to monitor for the AAVSO and also the most difficult to monitor for anybody else. For most sky surveys, you saturate at about 10th magnitude, so they aren't going to be able to monitor these stars. So it's a great place for us to be involved. As you can see, at this point, a year and a half in, or close to it, we have at least monitored every star a little bit. 192 have been observed, some of them better than others. We definitely need to work on that, but this has been overall a success. We have almost 30,000 total observations. We have 289 unique observers who have contributed data in some form or fashion. And this is just an example of why long period coverage is necessary here. You can see this has been going on basically since the beginning of the campaign. And until maybe 50 days ago or so, all it had been was a downwards trend. But as you can see, it does turn over eventually. I believe the star has like a 660-day period. So being able to monitor this and look for interesting changes in it requires these long-term light curves, which are virtually impossible to get any other way except for through observers like you. And here are just a couple other examples of some interesting ones that we have seen in the campaign. As you can see, red supergiants are not really, 2 things are very obvious. The first is that the variability that you see is not in any way the same from object to object. It can change a lot. It can also change a lot in the amount that it changes. And all of these things, because they're very, very big stars, means they change over very, very long time scales. So even over the course of the campaign so far, which is like 500 days or so, we've only really seen like, maybe one period of a lot of these cycles. So it is interesting to do, but obviously more results to come, and the longer we observe, the better. So with that, I will pass it on to George Silvas to give a bit more information.
Greetings. Okay, am I live? See the SNEWS campaign?
I don't see your screen yet, so you'll have to
Oh, there's another button to push.
yeah.
Okay.
Yep.
So for the AVSO, this is the kind of the central or the home page for the project. And you can just search for avso.org SNEWS-campaign. And this describes all the elements, a lot of the material covered by Dan and Bert. So this is a place to start for expanding your understanding. Now, to augment the call for observers to go pick a star and start observing it, what we've done with the AVSO net, which is a network of 9 telescopes around the world, we've tasked them to automatically go through that list of stars and continuously observe it. And what we do is that we invite people to come and sign up for the outflow for these targets. So whenever observations are taken of VE cam, they're sent to Andrew, CANG is his OBS code. So using this spreadsheet, you're able to sign up for stars and say, hey, nobody's signed up for this star. It's currently being handled by Dan Milisavljevic, but he'd be glad to have somebody sign up, and then you would automatically get NSV 13 stars coming to you via VFOT. And then you could do the photometry and then contribute it in. So far, this process, this subscription project, has generated some 13,000 images and 6,300 CCD CMOS observations in the AID. And it's been well received. We've had 25 different people who have signed up, and you can sign up for multiple stars. So it's very good participation. And there's still a number of stars which can be signed up for. If somebody wants to say, hey, that's something I can do, let somebody else do the observing, let me do the data processing. Come in and add your name here. Then what I do is I transfer it over to this column, and then the images start flowing. Any immediate questions about this process? Maybe not. I think that's mostly what I wanted to talk about, this subscription project, and hopefully we'll be sending images to more people. Are we frozen? Nope, Dan moved.
No, we are good.
Okay.
Thanks. Okay, so we can move back to questions and make more of this a sort of open discussion. They're coming rapid fire, so I will try to get to them as much as I can. So,
Bert, sorry, I just want to jump in. George, were you not going to show that cool camera setup?
Sure, let me do that. Bert, let me share.
I don't interrupt you, Bert. I just wanted to, I was really eager to see George's setup.
That's fine. Please go ahead. You should still have permissions, George. You can just share.
It's not. Am I? No, I don't think I'm on. There we go. So I've been fiddling around with a small telescope, something that I could have standing in the corner, ready to, when the alert comes in, just grab it and go. Some of you might recognize this. This is a Mighty Mini that people use for occultation observing. So the objective is half of a binoculars, and then there's a video camera here. So when the word comes, I can just grab this. I'll have sorted out orientation so I know that it's properly aligned. This is a tracking mount. So once it's set, it should be able to go. And then the goal would be to hook this up, running in video mode, and make sure it's got a couple terabytes of storage, and just let it go continuously. So when that thing brightens up, everybody will be begging for my light curve. So it's kind of like a volunteer fireman.
Nice. Okay, so let's
I love it, George.
Let's see. I will take a couple of questions that are more on the project side, and then we'll kind of just go back and forth. So someone asks if George, could you explain a bit more about what happens when you sign up for one of these stars, and also if you want the measurements to be transformed, or do they need to be transformed?
Okay. Yes. So the process to sign up is simply put your OBS code in the AAVSO net requesters column. Andrew pointed out to me that there's a problem with permissions, so you can contact me via a Slack channel or email, but I'll get your OBS code in there. Once that happens, then whenever images are produced for that star, they'll be you'll get an email. You've got data, and the images will be transferred to your VFOT account. And there you can play with them. You can examine them and say, oh, they need to be adjusted, they're not exposed long enough, or I need more images to get a proper SNR, give us feedback and we'll adjust, because you end up being the observer once you have the images in your hand. If you want to transform the data, these are all AAVSO net telescopes. They all have transform coefficients available in VFONT. So please do transform.
Cool. There were a couple of questions, George, on where exactly that spreadsheet is, and also one on whether you need to use AAVSONet or you can use your own telescope, and I'll answer that. You can definitely use your own telescope if you have one. We would love those observations. The AAVSONet project was set up because a lot of people wanted to contribute and they wanted to push things into AAVSONet, but with 192 targets, it's difficult for someone to put in a campaign for one thing. It was, people would put in for various stars, but there was a lot of overlap. So instead of doing that, we just decided to set up an easier spreadsheet so that people could, more easily pick it and we would get better overall coverage.
One thing to note is in that spreadsheet, which you can get to from the SNEWS campaign webpage, there's also a column that if you're not signing up for an AAVSONet subscription, but you can put in your obstacle and say, by the way, I'm observing this one. And so you get some idea of what other observers are doing. So those are for the people who want to use their own equipment and help balance the load.
Yeah, so if you, I will just go there real quick. So let me, I can go to my desktop and share. And let me get out of here. If you go to,
Bert, as you're putting that in, I just want to highlight how beautiful those light curves are. I talked about how after the explosion, it would serve great science opportunities to study the historical light curve, but there's already emerging great science opportunities to use these light curves to understand red supergiants more. I mean, the accumulation of this data has many purposes that can be exploited.
and in the chat, I just put the link to this. All of the SNEWS stuff you should be able to get to from here. The spreadsheet, the sign up for the fire drill, all of that should be on here. And if you don't see something, let me know, and I will make sure it gets fixed. You can send a message to aavso@aavso.org at any point, and I will find it. And I'm sure I will get it there if no other place. Okay. Let's see, where are we? So here's an interesting question for you, Danny. Why do localization regions look like two symmetrical spots on the map? Is it just a coincidence, or is there intricate mathematical, physical reasons behind it? If
It's just
it would be the Earth, right?
It's the way that the localization works, the triangulation works. You basically get these annuli between any facilities, and the way that the annuli kind of conspire to each other, you end up getting those kinds of regions. Yeah.
And a second one asking if the neutrino detectors are still gallons of chlorine tanks underground, or if they have changed the chemical makeup.
So different facilities are doing different types of science. You do everything from those that are trying to find dark matter to those like Super Kamiokande that are really designed for supernova follow-up, would have these big vats of water. So yeah, it depends on the neutrino facility. If you go to the SNEWS 2 site, they actually have a description of each of the experiments and the type of apparatus that's used.
Okay, and I see a couple of questions asking, hey, I'm a visual observer. Can I be of use to this project? And the answer is absolutely yes. So What you will notice is that we took the brightest stars in the sky, anything above 10th magnitude. However, that means that some of these stars are extremely bright and very difficult to do, even with small apertures. For instance, you can look at something like Alpha Orionis. There are a lot of people that do that. Most of them have specialized equipment to do it because it's very, very bright and it's difficult to do. It's something that is difficult to do with AAVSO net as well, because getting the exposures on very short things is also hard. So especially above 5th magnitude, all of your visual observations are very good because it's almost impossible to get those any other way, or it requires a lot of specialized effort and attention, which generally people aren't willing to do unless there's a really good reason for it. So those are great places where you can contribute, where we have very little information right now. The next question was, I had something up here. Oh yeah, someone asked about the application itself and how does it export the relative pointing data for the rigs?
Sorry, that's a question for me asking about the SNEWS app, the mobile app.
Yeah, I think it's saying, I think it's trying to ask, like, how does it give you the data for where the telescope should be looking? Like, I guess the format.
It's not connected to telescope software. It's purely a informational visual, kind of like Star Walk or any of the apps that you have. It helps guide you where the general direction is. Okay, that could be something we could discuss in the future. I don't think we'd want to make a native app trying to communicate with a variety of telescope mounts, but certainly that's part of the conversation, is what formats can we distribute these target lists to make it as quick as possible for you to get on target, right? So for instance, George, maybe you want to talk through what would be your workflow to get that camera pointed to where you want it to go.
As soon as it comes in on my phone, you hold it up and you figure out if you're looking down and that's where it is, well, then you've got 12 hours. It's on the other side of the world. But if you quickly locate that it's feasible, and if the telescope is in the corner and hasn't been moved by the cleaners, grab and go. To figure out, no, since this is a wide field view system, I'd go for just a static setup.
Exactly. It's pretty generous on where as long as you have the general direction, you'll be fine, right? Yes.
And then go ahead and grab the second telescope. I have one of those C-Star S50s. Perfect. Just because you can set it up, it'll figure out where its orientation very quickly, and then you can dial in some coordinates to it. You can get the coordinates of some of the targets by going to the spreadsheet, or we'll be publishing APIs that you could go say, here's the location, which of the 192 stars are in the field of view. And then,
that's right. So AAVSO has been working on that capability. So it's like a website resource where, you can find which stars are overlapping. By signing up for the fire drills, we're hoping to provide a more like direct to customer and even tailored listing of stars, and eventually coordination between them. That comes as a CSV file. Perhaps there are other formats that we want to think about. It's pretty straightforward. Once we have a common format, we just have to adjust the output to be compatible with that software. So to answer the question, the app as it is, it only points you in the right direction, doesn't connect to telescopes, but we would like to work with the users designing the output of the listing of targets that are best for them. And maybe we need some similar API that could be for that.
I see a couple of questions about spectroscopy, and the answer is that we will probably do spectroscopy in the future, and we definitely want it if you can do it. It just is a lot harder to manage. So If you would like some specific targets, maybe that would be a good fit, let me know, and we can maybe figure that out and see, because I would like to, focus in on a couple of them as opposed to just scattershotting around, and try to pick some targets that might be the best for that. And someone asked if their setup would work. I honestly am not sure. I don't know. Yeah, it was send that question, Richard Brown. Send that question to the AAVSO, and I'll try to answer it offline because I don't think I'll be able to do it here. Someone said their field of view is only 1 degree. What's their best strategy?
Yeah, that would likely be following up targeted stars and patrolling from the list.
There's another question, sorry, I have to read that. SB&D on SNEWS. I'm not sure what SB&D is. I thought it was too small and also not very useful as a surface detector. I worked on SB&D, so I am interested. I'm not sure what SB&D is. Do you know?
I can't help you there. They could follow up with an email,
Yeah.
if possible. Yeah.
Yeah, please do, because I'm not sure what to do with that. Okay. I think we'll take one more question we can do, and then I will move into the outro. So it says, maybe I missed this, but the Andromeda Galaxy is the Andromeda Galaxy also being continually monitored in some fashion to catch a supernova? I think that the only supernova seen in outburst in Andromeda happened in 1885, and it was a type 1A.
Yeah, again, another 1A. That's right.
So I don't, I know the SNEWS project isn't directly monitoring Andromeda. Is anybody else?
The closest would be the all sky surveys that are monitoring. And then there are some surveys that are targeting nearby galaxies within 40 megaparsecs. That's the one running by David Sand out of University of Arizona. I haven't looked at their list, but I imagine that may be one of them. But then again, it's a big field of view. It's actually interesting. I would first guess that no, they're not looking at that regularly, but I could be wrong.
Okay. I think that is all we have time for today. I'd like to extend again a very big thank you to Dan Milisavljevic for their time and expertise on the SNEWS network. We are very happy to have you come in and talk about this. It's a great, exciting project for the AAVSO. I would also like to thank our sponsor again. Boise Astro has sponsored our entire 2025 webinar series. Boise Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at boise-astro.org to learn more. I'd like to thank everyone in the audience who joined us during today's webinar. Your excellent questions really helped to make today's session something great. More than that, your participation in all of our programs is what allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you, each of you. We are so grateful for your support. Today's broadcast has been recorded. And if you'd like to go back and reference the recording, you can find it on our Facebook page. Pretty soon, we will also upload it to our YouTube channel, where it will join our enormous library of educational videos. You can find our library on YouTube by searching for the username AAVSOHQ, and it should be up sometime this week if you'd like to find it. When you leave, you should be automatically shown a survey. I would really appreciate it if you could fill it out to let us know your thoughts on today's session and what we could do better next time. Our next session will be Deciphering Eclipsing Binaries, presented by Dr. Pierre Maxted. But that is it for today's webinar. One last huge thank you to Dan and to George for being here for this and for supporting this program. We really appreciate it.